In the previous lectures, we have derived the Newton-Cotes integration rules, in particular the trapezoidal and the Simpson's rules. We have also derived the composite trapezoidal and Simpson's rules. The extrapolation schemes which we called as Romberg integration are very useful to obtain results which converge very fast. Now, each column in the Romberg integration table is of at least of one order higher than the previous column, but in the case of the trapezoidal and Simpson's rules, these were 2 orders higher than the previous column. In the case of the trapezoidal rule, if the actual result of order of h square, then the first extrapolation gives us an order of h to the power of 4, then the next extrapolation goes to order of h to the power of 6 and so on. Similarly, for the Simpson's rule. Therefore, the Romberg integration rule is one of the most powerful rules to get the results which converge very fast. In the case of the trapezoidal rule or the Simpson's rules, we have taken the abscissas, that is x 0, x 1, x 2 as fixed. Therefore, we were able to use the Legendre interpolation formula and then construct the Newton-Cotes formulas. However, if we want to increase the order of a method, it is necessary that is for us to consider the abscissas also as unknowns and determine the unknowns, so that the order of the formula can go up with using less number of points only. What we are saying is, in the trapezoidal rule, it is a 2-point rule if we started with, and the 2-point rule has given a formula of precision 1, because it integrates exactly polynomials of degree 1, whereas in Simpson's rule we have used 3 points and it has given us a formula with precision 3, that is polynomials which the integration rule which integrates exactly polynomials degree less than or equal to 3. However, if I now allow the abscissas also to be unknowns and determine them, it is possible for us to raise the order of the formula with less number of points. Such formulas are called the Gauss integration rules. So, let us now consider the Gauss integration rules. Therefore, what we are looking for is a formula of the type integral a to b weight function w x f x dx is approximately lambda naught f of x naught plus lambda 1 f of x 1 plus so on lambda n f x n. Now, we shall allow x case as well as f case unknowns. So, we will take x k and lambda k are unknowns to be determined, and k going from 0, 1, 2 to n. Therefore, here we have n plus 1 unknowns, here we have n plus 1 unknowns, therefore, we have a total of 2 n plus 2 unknowns. We have 2 n plus 2 unknowns to be determine this particular formula. Hence, a formula of order or precision 2 n plus 1 can be determined. Therefore, we can say a formula of order 2 n plus 1 can be determined. Now, it is indeed true that a formula of such order really exists, and we can derive that particular formula such that this n plus 1 point rule can become a formula of order 2 n plus 1. Now, the basic theorem for this is that if I choose these abscissas x 0, x 1, x 2, x n as the zeros of an orthogonal polynomial, orthogonal with respect to the weight function w x over the interval a to b, then it is possible for me to construct a formula of this type with precision 2 n plus 1. Depending on the weight function and the interval of integration, we can construct the corresponding orthogonal polynomials. The most important orthogonal polynomials we know are the Legendre polynomials, Chebyshev polynomials, if you have finite interval -1 to 1, or if we have Legendre polynomials in 0 to infinity, Hermite polynomials in -infinity to infinity. So, we have the orthogonal polynomials available to us. These orthogonal polynomials can be used to construct the integration rules of the order 2 n plus 1 over here. this result which I stated, let us take it as a theorem. So, let us call this as a theorem. If x k are selected as zeros of an orthogonal polynomial orthogonal with respect to, I will write down WRT so that it is with respect to the weight function Wx with respect to the weight function Wx over the given interval a b, whatever the interval that is given to us, then the formula 1 has precision to n plus 1. That means, it is exact for polynomials of degree less than or equal to 2 n plus 1. It is going to integrate exactly polynomials of degree less than or equal to 1. And another important thing is, further all weights are positive, all weights lambda k are greater than 0. Therefore, what we are stating here is that in this particular formula, if I choose these abscissas x k's as the zeros of an orthogonal polynomial orthogonal with respect to this weight function that is given to us over the given interval a b, then it is possible to get the precision of 2 n plus 1. Let us start the proof of this with assuming that f x in our integral is a polynomial of degree 2 n plus 1, and then we shall show I can get the values of lambda k and x k uniquely from there, then that means we obtain the required result. So, let us say let f x be a polynomial of degree 2 n plus 1. Now, x k and f x k are unknown. So, let us take this as our data points, I is equal to 0 1 n or n plus 1 set of points. So, I am taking the abscissa and the corresponding ordinates, and then I will take this as n plus 1 set of points. Now, this is excise or random here, arbitrary, they are not of equal length. Therefore, what I will do is I will construct a Lagrange interpolating polynomial passing through this. This is n plus 1 set of points, therefore, I can get a polynomial degree less than or equal to n passing through this one. So, let us say let q n x be the Lagrange interpolating polynomial, interpolating of degree less than or equal to n, interpolating this data. So, we have taken these points abscissas corresponding weights, then we call them as n plus 1 set of points, and then using this n plus 1 set of points we are constructing the Lagrange interpolating polynomial q n x of degree less than or equal to n. So, that means q n x is of the form, therefore, q n x will be of the form our Lagrange interpolating polynomial, it will be summation of k is equal to 0 to n L k x f x k, where L k x are the Lagrange fundamental polynomials, which we had written it as pi x upon x minus x k pi dash of x k, and pi of x is the product of all the factors x minus x naught, x minus x 1, x n. This is the factor. This is the Lagrange interpolating polynomial interpolating at the n plus 1 data points given to us, and these are the Lagrange fundamental polynomials that we are using it. Now what we will do is I would construct a new function. So I will consider a function let us call it as gx. This is equal to fx minus qnx. Now we know that fx is, we started with a polynomial of degree 2n plus 1. This is a polynomial of degree 2n plus 1. Now this is a polynomial of degree n. This is a polynomial of degree n. What happens at x is equal to xi? I will have g at xi is equal to f at xi minus qn at xi. Now qnx is a Lagrange interpolating polynomial interpolating at the data, and hence it is exactly equal to f xi. Therefore this is equal to f of xi minus f of xi, that is equal to 0 for all I. This is obvious because qnx is the Lagrange interpolating polynomial interpolating the given data, and therefore this is equal to f at xi and this is equal to 0. Therefore this implies that our function gx has n plus 1 zeros at x0, x1, x2, xn, because g at x is equal to 0 at these points. Therefore this implies that gx has n plus 1 zeros at x0, x1, xn. What does that mean? These are n plus 1 zeros, means x minus x0, x minus x1, x minus xn can be factors. Therefore x minus x0 so on x minus xn are factors of gx. If that is so, their product is a factor of gx. Obviously the product is a, therefore the product, their product, let us call this as Pn plus 1x. Let us put me a star, Pn star x minus x1, x minus xn is a factor of gx. I will now choose a polynomial of degree n plus 1, polynomial of degree n plus 1 such that is a polynomial of degree n plus 1 such that P n plus 1 x I is equal to 0, I is equal to 0, 1, 2, so on n. Both will be the same if the leading coefficient of P n x is 1. Here if I open it up, expand it, the leading coefficient is x to the power of n with leading coefficient is 1. P n plus 1 I am allowing leading coefficient to be something arbitrary. For example, if you have a quadratic, you may have 3x square minus 2x plus 1. So the leading coefficient is 3. So therefore in P2 I am allowing the leading coefficient to be a factor which is not equal to 1, whereas if I take this simply as factors and multiply it out, the leading coefficient will be 1. So either one of them can be taken because Pn plus 1 xi is automatically 0, therefore this has got the same factors. If that is so, we have said that the this product is a factor of gx. Therefore I can write down gx as equal to, which is we started with fx minus qnx. This is the definition of this. This can now be written as Pn plus 1x. Now gx is a polynomial of degree 2n plus 1. I have taken out n plus 1 polynomial degree polynomial. Therefore, what is left out will be polynomial of degree n. Therefore, it will be some r n x. It will be some r n x, where r n x is a polynomial of degree n. This will be polynomial of degree n. So, that the total degree is 2 n plus 1, which is the degree of the polynomial g x. Now, this is the basis of our theorem. Let us number is 2. Let us multiply both sides by the weight function and integrate over a b. So, multiply by the weight function w x and integrate. Now, that will give us, I am just multiplying both sides by w x and integrating. Therefore, I will have integral a to b w x f x minus q n x dx, and that is equal to integral a to b w x p n plus 1 of x r n x dx. Now, we shall open up the left hand side and simplify, take this to the right hand side. So, I will write this as integral a to b w x f x dx is integral a to b w x q n x dx plus the second term integral a to b w x p n plus 1 x r n x dx. So, I have just separated out this into two integrals, sum of two integrals, taken one integral to the right hand side, that is w x q n x to the right hand side, and added to this one. Now, choose this p n x that we have taken here, p n plus 1 x, this or this, choose this as an orthogonal polynomial, orthogonal with respect to weight function w x over the interval a b. If I choose p n x as an orthogonal polynomial, what would happen? We know if you have an orthogonal polynomial sum q I x, then integral a to b w x q I x q j x dx is equal to 0 for I not equal to j. Therefore, if I once choose this as an orthogonal polynomial, then this is a polynomial of degree n, this is a polynomial of degree n plus 1, hence by the property of the orthogonal polynomials, the value of this integral is 0. Therefore, now choose p n plus 1 x as an orthogonal polynomial, of course of degree n plus 1, as an orthogonal polynomial, orthogonal with respect to the weight function, with respect to the weight function w x over a b. That means, integral a to b w x p n plus 1 x, any polynomial p j x dx is 0, j not equal to n plus 1. If j is not equal to n plus 1, then this is going to be 0 by the definition of an orthogonal polynomial. Now, in our integral we have the r n x as a polynomial degree n, therefore, this integral will be 0, therefore, I will just have this expression as my result. Therefore, I conclude from here integral a to b w x f x dx is equal to a to b w x q n x dx. Now, we have achieved what we want, we have thrown away the second term, and we have got this, but Qnx is known to us already, it is the Lagrange interpolating polynomial. So, I can substitute the value of Qnx. So, if I substitute it, I will just get simply I will have we have written k is equal to 0 to n integral a to b wx lkx dx into f of x k. I substituted the value of Qnx, that is your lkx fxk, integrate over a to b, fxk is independent of integral. So, I have written it out of this one, and this I will write it as lambda k fxk. Which is our required formula, where your lambda k is integral a to b wx lkx dx. This formula looks identically same as we have done in the Newton-Cotes formula, except that here the abscissas to be chosen are the zeros of an orthogonal polynomial. There we have in trapezoidal Simpson's rule we have fixed the abscissas already, but here when once you choose them to be the zeros of an orthogonal polynomial, the order of the formula goes up. Now, either I can use this Lkx as a fundamental polynomial, or I can write Lkx back in terms of Pn plus 1x that we have chosen. So, I could as well have written this as a to b wx, and I can write Lkx as polynomial Pn plus 1x divided by x minus xk Pn plus 1 prime at xk dx. Now, what we had really written here is that Lkx are given by this. This numerator pi x is nothing but x minus x naught x minus xn. So, in place of this we are now using that Pn plus 1 x, which we had derived it here as Pn plus 1 star is this product, or if this has a leading coefficient, we allow the leading coefficient to be there, and that leading coefficient shall cancel with the leading coefficient it is there. If there was a 3 leading coefficient, there is a 3 here also. So, that 3 cancels off, and this ratio would be identically same as the Lkx. So, either I can actually use Lkx as determined by this, or I can take the whatever the orthogonal, because Pn plus 1 is an orthogonal polynomial. So, I can insert the orthogonal polynomial itself here in place of writing Lkx, integrate this and get my lambda case. Now, this since we are able to uniquely determine lambda case, this shows that fx is indeed a polynomial of degree 2n plus 1, and hence the formula is of precision 2n plus 1. Therefore, we can say xk and lambda k are determined uniquely. And therefore, fx is a polynomial of degree 2n plus 1. Therefore, the formula has order 2n plus 1. Therefore, the formula has order 2n plus 1. We have to show that lambda case are positive. But before that, let us see what this implies. Let us suppose I take 2 point formula, say n is equal to 1, 2 points. This corresponds to the trapezoidal rule in the fixed abscissa case, and what will be the order here? The order is going to be 3. N is equal to 1, therefore 2n plus 1, that is order 3. That means the corresponding to the trapezoidal rule we have there, we have here which is order 3, there it is order 1. If I take n is equal to 2, that is 3 points, this corresponds to the Simpson's rule in the case when the abscissas are fixed or pre-chosen, but here we have the order as 5, 2n plus 1 order is 5. So, you can see the order is 5 here, Simpson's rule is only of order 3. So, the order of the formula shoots up like anything when you allow these abscissas to be not equispaced, but they will be arbitrarily spaced, but they would be zeros of an orthogonal polynomial. Now we shall show that lambda k's are positive. Now since it is integrating exactly polynomials of degree 2n plus 1, it will also integrate any polynomials which is less than that degree. Therefore let us choose f(x) as simply Lj square x. Ljx is a Lagrange fundamental polynomial which is of degree n, hence f(x) is a polynomial of degree 2n. Therefore this formula should integrate this exactly. The formula integrates exactly. That means integral a to b wx Lj squared x is summation k is equal to 0 to n lambda k Lj squared x k. But by definition Lj square x k all zeros except j is equal to k. Therefore this is equal to simply lambda j, all of them would vanish except one where j is equal to k and that is equal to 1. Therefore this entire sum is simply equal to lambda j. Now wx is a weight function positive quantity, Lj square is a positive quantity, b is greater than a, therefore the value of the integral is always greater than 0. Therefore this implies that lambda j is strictly greater than 0. So that all the weights are positive, and what is the advantage? The advantage is that there will be no errors due to cancellations, because if the weights, sum of the weights are negative, then there will be cancellations, then there will be growth of errors. We shall now derive some Gaussian integration rules using the known orthogonal polynomials. We shall derive 1 point, 2 point and 3 point integration rules and then generalize them. Let us first consider the derivation of Gauss-Legendre formulas. As the Gauss-Legendre formulas, these are called the Gauss-Legendre formulas. The Legendre polynomial is defined on -1 to 1. Therefore, given an interval a b, reduce it to -1 to 1 by using a linear transformation. So, reduce a b to -1 to 1 using a linear transformation. That is something like we are putting x is equal to some p t plus q, you are putting x is equal to p t plus q, then when x is equal to a, t is -1, so that is p plus q, when x is equal to b, t should be 1, so that is p plus q, I can add these two, I find the value of q. Therefore, q is equal to a plus b by 2, and I can subtract these two, b minus a by 2 is p, b minus a by 2 is equal to p. Therefore, the required linear transformation, which we can always remember it easily as half of b minus a into t plus b plus a. So, this is the transformation, linear transformation, which will reduce a b to the interval -1 to 1. Further, we will take weight function as 1. Now x is lying between, now we are taking the dummy variable as x, now we are replace it by t and replace t by the dummy variable x. Now, so we will talk in terms of x only. So, x is lying between -1 to 1. the orthogonal polynomials which are orthogonal over minus 1 to 1 with weight function 1 are the Legendre polynomials. Therefore, the p n plus 1 which we are talking of in the rule is the Legendre polynomials p n plus 1 x. These are the Legendre polynomials. These are the Legendre polynomials. Now, we have earlier discussed the orthogonal property of the Legendre polynomials. We have shown it as minus 1 to 1 some p m x p n x dx is equal to 0 for m not equal to n. Now, let us recognize our values of x k and lambda k. X k's are zeros of p n plus 1 x, the zeros of p n plus 1 x. That means, if you want a particular formula, fix up your n, find out what is the Legendre polynomial, find its zeros, and those are will be the abscissas in our formula. And lambda k would be equal to, we have derived that lambda k is equal to w x p n plus 1 x upon this. So, I could write this as integral minus 1 to 1 w x that is 1 p n plus 1 x, this is the Legendre polynomial, divided by x minus x k p n plus 1 prime at x k dx with w x is equal to 1. Now, that is all we need. We know what will be x k's, what will be the weights of this, and once this is known, I can substitute in the formula. Then these formulas are called the Gauss-Legendre formulas. Now, let us derive some particular formulas. Let us write down one point formula. Now, one point formula means n is equal to 0, and I have to consider p n plus 1, that is p 1. So, I must consider p 1 x which is equal to x. The abscissa will be obtained by setting p 1 x is equal to 0. So, p 1 x is equal to 0 gives x is equal to 0. Of course, I should, so there is no confusion, w x is 1. Now, let us substitute what is our lambda 0. Lambda 0 will be minus 1 to 1 numerator p 1 x that is x, x minus x 0 that is x, derivative of p n p 1, derivative of p n is 1, that is equal to 1 dx. This is p n plus 1, that is p 1, this is p 1 prime, this is x minus x 0, that is simply x, that is simply integral dx, that is equal to 2. Therefore, we have derived the formula minus 1 to 1 f x dx is equal to 2 times f of 0. Lambda 0 is 2, x is equal to 0, therefore 2 times f of 0. And what is the order of the formula? That is 2 n plus 1, that is 2 into 0 plus 1, therefore order is 1. So, this is the one point formula. Let us take a 2 point formula. So, then I will have n is equal to 1. Therefore, I have to choose my p 2 x, the polynomial will be p 2 x, p n plus 1, that is your p 2 x. P 2 x is equal to half 3 x squared minus 1. Now, the roots of this is, if you set it equal to 0, you will get x squared is equal to 1 upon 3, therefore, x is equal to plus minus 1 upon root 3. Therefore, the abscissas are x 0 is minus 1 upon root 3, x 1 is 1 upon root 3. In terms of x 0 x 1, let us write down what is our p 2 x. Now, this is what we were stating when we were proving the theorem, that this one may have a coefficient in the leading power of x. Here we have a coefficient of 3 by 2 here, and it is not 1. So, what we will have here is 3 by 2 x minus x 0 into x minus x 1. So, if I take out factor from here, the roots are this x 0 and x 1. So, this is same as 3 by 2 x minus x 0 into x minus x 1. Now, with this I would like to find out what are our weights. So, let us find out what is the weight lambda 0, minus 1 to 1, this is p 2 x. So, this is 3 by 2 x minus x 1. Now, I have saved one step, because there is denominator is x minus x 0 here. I have cancelled x minus x 0, I have not written that. And let us write down one more step here. What is our derivative of this? P 2 dash is equal to 3 by 2 into 2 x, that is equal to 3 x. P 2 dash is equal to 3 x. Therefore, this is P 2 dash at x k, that is P 2 dash at x k, that is 3 times x 0. We are talking of lambda 0, so I will have this as x 0 and dx of course. Therefore, this is 3 by 2 into 1 by 3, x 0 is a constant and x 0 is minus 1 by 3. So, let us take it out, minus root 3, yes, x 0 I have taken it up, integral of minus 1 to 1 x 1 is 1 by root 3. So, x upon 1 by root 3 dx. So, I have here minus root 3 by 2, I cancel through this one, x dx is an odd function, therefore, it is 0. So, the contribution will come only from the second factor, and that is minus 1 upon root 3 into integral of dx, that is x, that gives you 2. Therefore, this is equal to simply 1. Now, let us write down lambda 1. Lambda 1 is minus 1 to 1, again I will have numerator as 3 by 2, this time I will have x minus x 0 dx, x minus x 1 has cancelled, denominator will be p 2 dash at x k, that is p 2 dash at x k, that is 3 x 1 dx. Now, this is let us cancel off 3, and this is 1 upon root 3. So, therefore, root 3 by 2, and again integral x dx is 0, it is an odd function. X 0 is minus 1 by 3. So, this is plus 1 by root 3 into 2, minus x 0 is minus 1 by 3. So, I will have plus 1 by 3, integral of dx is 2. So, this is also equal to 1. Therefore, the 2 point formula, Gauss Legendre formula, is minus 1 to 1 f x dx, both the weights are equal and that is 1, therefore, we have f of minus 1 by root 3 plus f of 1 by root 3. And what is the order of the formula? Is 2n plus 1, that is 3. So, the order of the formula is 2n plus 3. Now, you can compare with the trapezoidal rule, which uses 2 points which are fixed points, and now we have got a formula of order 3. Now, I can quote the 3 point formula also, because we often use the first 3 formulas, 3 point formula, that is n is equal to 2. Therefore, I must choose the orthogonal polynomial Legendre polynomial P 3. So, I will take P 3 of x, that is half 5 x cubed minus 3 x, 5 x cubed minus 3 x. Therefore, if I set it equal to 0, I will get here is x into 5 x squared minus 3 is equal to 0. Therefore, x is equal to 0 and plus minus 3 by 5 under root of this, that is under root of 0.6. So, I can use this as under root of 0.6. Therefore, the 3 abscissas are x 0, I will first take the negative value under root of 3 by 5, x 1 as 0, x 2 as plus under root of 3 by 5. Now, I will leave this as simple exercise for you, just as we have substituted lambda, we can find out the value. I will give the values, just find it out. Lambda naught comes out to be 5 by 9, lambda 1 is equal to 8 by 9 and lambda 2 is equal to 5 by 9. So, that the formula, the 3 point formula is given by f x dx is 1 upon 9 5 times f minus under root of 3 by 5, 8 times f of 0 plus 5 times f of under root of 3 by 5. And the precision of this formula or the order of this formula is 2 n plus 1, n is 2, therefore, order is 5. Now, we can compare this with the equispaced Simpson's rule, wherein the order was 3, with 3 points we have got a formula of order 3, now we have got a formula of order 5. Now, let us illustrate this through an example. Let us take an example. Evaluate integral 0 to 2 dx upon x square plus 2 x plus 10 by Gauss Legendre 2 point and 3 point formulas. Now, compare with the exact solution. Suggest a way to improve the result obtained. Now, to apply the formula, we notice that the interval given to us is 0 to 2, that is a and b. So, we must first of all reduce it to minus 1 to 1. So, we have been given the interval as a b is equal to 0 2. Now, this is always a linear transformation, therefore, I can straight away write down what is my transformation here, which reduces to minus 1 to 1. So, I can immediately write down that x will be equal to half of b minus a into t plus b plus a, that is equal to t plus 1. So, this is the transformation that is required. You can verify when x is 0 t is minus 1, when x is 2 t is equal to 1. So, we have reduced it to the required formula. Therefore, our f x, let us call it as now g t, that is equal to 1 upon x square, that is t plus 1 square 2 times x plus 10. So, I am just substituting in this t plus 1 whole square 2 times t plus 1 plus 10. that is equal to 1 upon t square plus 2t plus 2t, that is 4t, 1 plus 2 plus 10, that is 13. Therefore, our function g t is this. Further, in our integration, dx is equal to dt, dx is equal to dt. Therefore, our integral, let us call it as I, 0 to 2 dx upon x square plus 2x plus 10 is equal to minus 1 to 1 dx is equal to dt, and we have just derived this is t square plus 4t plus 13. Now, we shall apply our 2.3 point formulas on this integral minus 1 to 1 f t dt or some g t dt. Therefore, what we I think we call this as g t. So, let us call this as minus 1 to 1 g t dt. Now, let us use the 2 point formula. Therefore, value of the integral I is equal to g of minus 1 by root 3 plus g of 1 upon root 3. So, I just substitute the values and then evaluate it. So, this will be simply 1 upon 3 minus 4 upon root 3 plus 13, and this is 1 upon 3 plus 4 upon root 3 plus 13. Now, this I will use for the next value. Therefore, I will give you these values. These values are 0.9, 0.71 plus 0.06, 393, 0.15, 464. So, with the 3 point formula, I will be equal to 1 upon 9, 5 times f of minus under root of root 6. I will now use 3 by 5 as 0.6, 8 times f of 0, 5 times f of root of 0.6. This is 0.15455. 'Now, let us try to find the exact solution of the problem. Our integral is 0 to 2 dx upon x square plus 2x plus 10. This I can very easily write it as dx upon x plus 1 whole squared plus 9. Therefore, this is 1 upon 3 tan inverse of x plus 1 by 3 within the limits 0 to 2, that is 1 by 3 tan inverse of 1, that is pi by 4 minus tan inverse of x is 0, 1 by 3, and if you compute this, this is 15455. 3 point formula is exactly matching with 5 decimal places, and the 2 point formula is matching for the first 3 decimal places. Therefore, the order of the 3 point formula was 5, therefore, it is integrated this very well. Now, the second question that we asked was that suggest a way to improve the result obtained. Now, we are not thinking of an extrapolation or anything. The accuracy of the formula would increase if I am able to break this into number of integrals, just as we have done the composite trapezoidal rule, in which to improve the accuracy the given integral is broken into number of integrals, and on each integral we have applied the trapezoidal or Simpson's rule. Same thing can be done here. Therefore, what we would like to suggest I will write down 0 to 2 for example as I will write it as 0 to 1 plus 1 to 2. I will write it as 0 to 2 as 0 to 1 and 1 to 2. Now I will reduce this to minus 1 to 1, this also to minus 1 to 1. This is like almost like a composite Gauss Legendre formula, it is like this. Now for this the AB for this is 0 to 1 and for this the AB is 1 to 2. Now I can write down the transformation for this to make it minus 1 to 1. So I can bring this to minus 1 to 1 of some gt dt and this I can bring it to minus 1 to 1 some ht dt by using the suitable transformation. Then I can apply the 2 point formula on this, apply the 2 point formula on this and the 3 point formula, the corresponding result will be definitely be superior to what we have obtained here in this particular previous case as these two results. It will be much more superior than this and of course we can carry on to number more decimal places and do this. It is something analogical to what we have derived the composite trapezoidal or Simpson's rule and this is the way of attaining the higher accuracy in the Gauss Legendre formulas. Even though we can exactly give the error, find out the error and give the error, however computationally if you want to have better results over an integral which is a very large, the length of the interval is very large, you can cut that into number of parts like this and then each one we make the transformation to bring it back to minus 1 to 1 and apply the Gauss Legendre formulas. Okay, we will stop at this.